So good morning, precalc friends. So a couple things before we get started on the lesson. One, thank you for doing a good job on watching that crazy guy with his video and his derivation of the Pythagorean identities. And also thank you and sorry for writing those identities, those basic identities 3 times each. I just wanted to make sure they got into your brain because we need to use them today. So thank you for that. And also, you should be thinking about what courses you're going to take next semester, next year, I mean. And so, yeah, calc is the way to go, man. It is the greatest math class ever. So, just putting that out there. All right, so let's use an identity to kind of help us to get through this, or a couple of identities to help us to get through this mess right here. So we see that the secant of some angle is -3/2, and we know the tangent is positive. So obviously we are in because tangent is positive, we're either in the first quadrant or we're in the third quadrant, and this says that this is negative, so we must be in the third quadrant. A little piece of useful information that may or may not come to pass in this problem. Okay, so the first thing I would do, and generally the best thing to do when doing any of this trig identity stuff, is try to get as many of the pieces into sines and cosines as possible, because everything is kind of built off of sine and cosine. So we know that secant of u is the same as 1 over the cosine of u. So we know that secant of u equals 1 over cosine of u, and that's equal to -3/2. And so what we want to do is we want to figure out what is the cosine of u. And so when we see two fractions like this equal to each other, we can flip both fractions over. And so now we know that the cosine of u equals -2/3. So that gets us the cosine. And as I said, it's best to try to work with sines and cosines as much as possible. So we have this cool identity that you learned about, and you saw the crazy guy doing his little derivation. So we know that the sine squared of u plus the cosine squared of u equals 1. And we know the cosine of u is -2/3, so we're actually going to square that. So we got -2/3 squared, and we got sine squared of u, and so then we have sine squared of u plus 4/9 equals 1. And then we're going to subtract 4/9 from both sides, and yeah, I'm going to run out of space here. Then we're going to get sine squared of u equals 1 minus 4/9, of course, is 5/9. And that means that the sine of u is the square root of 5 over 3. And because we are in the third quadrant, we know this is going to be negative. So that is 2 of our trig functions that we're interested in. There's the sine, there's the cosine, that's 2. We started with this, where are we? So that's 3. We got 3 more to go, but they're all easy from here. So we know from one of our other identities that the tangent of u equals the sine of u over the cosine of u. And so the sine of u in this case is -√5 over 3. And that's going to be over the cosine of u, which is -2 over 3. And when we flip and mult, we see that we're going to get √5 over 2. And that's a positive because we divide out negative by negative. That's a positive, and that is what it should be. It should be positive because tangent is positive over there. So there's our tan u. So that's that one. So now I have 1, 2, 3, 4, and we just need 2 others. And we know by the reciprocal identities that the secant is just the reciprocal of that. So we know the secant of u equals -3 over 2. that's number 5. And number 6 is just the reciprocal of this guy right here. So that's the cosecant. CSC of u equals -3 over root 5. But of course, we always rationalize. So we have -3 root 5 over 5. So I just barely squeaked that one in there. Okay. So again, try to turn everything into sines and cosines when we can. And so we used a reciprocal identity. Then we used a Pythagorean identity to get us to sine. And then tangent is just sine over cosine. And then we just, crap. What am I missing here? I'm missing 1, 2, 3, 4. Oh, crap, I already had secant. That's dumb. I didn't need that. What I needed was cotangent. Well, so the cotangent is just the reciprocal of this guy right here. So we just flip that over and rationalize that. So it's going to be 2 root 5 over 5. So sorry, I missed that one. But anyway, so that's the process. All right, so next we're going to simplify this expression right here. So here we see that we have sines, and I don't know what happened there. I don't know why that's there like that. Anyway, so we see we have sines and cosines, but what we want to do is we want to make them all into the same function. So we have more sines than cosines, and we know something about a cosine squared. We know that it's somehow related. So we remember that the sine squared of theta, or x in this case, plus the cosine squared of x equals 1. And now we know the cosine squared of x is just 1 minus sine squared. So 1 minus sine squared is cosine squared. So we're just going to use this and substitute into there. So now we're going to have sine x times 1 minus sine squared x minus sine x. And then we're going to multiply through, and we're going to get sine x minus sine to the third power, sine cubed x, minus sine x. And these guys are going to cancel off, and we're just left with negative sine cubed x. And there we go. Okay, again, the key is to try to turn everybody into sines and cosines and try to make sure that that your expressions have all or as many of the same type of trig function as you can. All right, put this off to the side. All right, so we're going to factor this. So you should recognize the structure here. We have a square minus a square. This is just the difference of squares. So just treat secant of theta just like a variable. So we got secant theta plus 1, and we got secant theta minus 1. This is just the difference of squares. And that's it. There's nothing to it. Nothing tricky about it. Just treat it like it's a variable. It is. It's just an unknown quantity. Okay. Same situation right here. Just treat tangent x as though it were a variable. So this is like 4x squared plus x minus 3. So what do we do there? Well, we ask ourselves, well, actually, this is going to be the master product rule. And boy, I didn't leave enough space for that. That's a funny one. All right, so can I do this? 6, 2, 4, 3. Yeah, it's probably going to be best to do it that way. Okay, so here's what I think is going to happen. So I have 4 tangent theta times tangent theta. Yeah, that's going to work. Because I know that 4 tangent theta times tangent theta makes 4 tangent squared theta. And then I need 2 numbers that multiply to make negative 3. And that's going to obviously be positive 1 and negative 3, or vice versa. So I'm going to put a plus 1 here and a minus 3 here, because 4 times 1 makes 4. Negative 3 times 1 makes negative 3. 4 minus 3 is 1. So there it is. We could have done this by the master product rule. And if you wanted to, you could change them all into x's and then change them back later. So you could write 4x squared plus x minus 3. Do the master product rule, and then wherever you see an x, put in a tan theta. But this worked out just very well here. Okay, so we want to factor this guy right here, and we'll again notice that these are not the same functions. Here we got cosecant squared theta, and we got cotangent theta. And of course we think, all right, is there some sort of identity that relates these two here? And as a matter of fact, there is. 1 plus cotangent squared theta is the same as cosecant squared theta. So we're just going to make that substitution right into there. So we're going to have 1 plus cotangent squared theta minus cotangent theta minus 3. And we just rearrange it so it's in descending order of power. So we got cotangent squared of theta minus cotangent theta, and 1 minus 3 is negative 2. And then we just need to factor this guy right here. Now you'll notice that they all are the same function. So we just treat them like they're the variables. And we ask ourselves what two numbers multiply to make 2, or negative 2, and add to make negative 1. And those, of course, are negative 2 and positive 1. And we are done. Easy stuff. Okay, so 3 more problems. All right, so we want to simplify this guy right here. And again, we see sine and cotangent and cosine, and how are we going to deal with all that crap? Well, again, we're going to try to turn everything into sines and cosines. So this is already a sine, that's already a cosine, so we know that there's an identity for this. Cotangent is the same as cosine over sine. So I'm going to do sine of t plus cosine of t over sine of t times cosine of t. Oops, crap, I got ahead of myself there. All right, so we're multiplying. And this is over 1, and this is also over 1. And so we see that we're going to multiply cosine t times cosine t. So now we have a sine t plus cosine squared t over sine t. Right, just multiplying bottom times 1. So when we see cosine squared of t and we see a sine of t, we think, oh man, wouldn't it be great if that was a sine squared of t, because then we can make a 1 out of that because of that identity. Well, as it turns out, if we're going to add these two fractions, we need to have common denominator. So the common denominator is obviously going to be sine t. That means I'm going to multiply this fraction here by sine t over sine t. So that's going to get us sine squared t plus cosine squared t over sine t. And, of course, sine squared t plus cosine squared t is just 1. So that's 1 over sine t. And we know that 1 over sine t is the same as cosecant of t by our reciprocal identities. And we try to write all of our answers in the simplest format possible, and so this is a little simpler than that. So we change everything into sines and cosines so that we can do the simplifying throughout the process, because again, everything's based on sines and cosines, but in the end, we want to write the simplest expression we can, and sometimes that involves a sine or a cosine, and sometimes it doesn't. Okay, so adding these two guys here together, it's going to be the same trick as we just did right up there. And so we are going to need a common denominator. So we got 1 plus cosine x, we got sine x. The common denominator is obviously just going to be the product of those two guys right there. So that means I'm going to multiply this guy by sine over sine, and this guy by 1 plus cosine over 1 plus cosine. So I think we can all do that in our heads, right? So we're going to multiply by sine over sine right here. So that's going to get us sine squared x over sine x times 1 plus cosine x plus, so now we're going to multiply this guy here by 1 plus cosine x. So that's going to get us cosine squared x plus 1 also over sine x times 1 plus cosine x. And we put these two guys together in one big fraction with the common denominator that's right here, and we see that sine squared x plus cosine squared x, we see that, and we recognize that as an identity, and that, of course, is 1. So sine squared plus cosine squared is 1, plus the other one makes 2. So that's equal to 2 over sine x times 1 plus cosine x. That is all we can do there. Okay, last problem. So we want to rewrite this guy here in a form that does not involve any fractions. So there's definitely a little bit of trickery here. And what you need to remember is the whole concept of multiplying by the conjugate. So for example, if we wanted to simplify 3 over 5 plus, I don't know, let's say root 2, and we wanted to rationalize the denominator, we would multiply by 5 minus root 2, right, the conjugate, 5 minus root 2. We're going to do the exact same concept right here with multiplying by the conjugate, and you'll see how slick that is in just a moment. Okay, so we're going to multiply by 1 minus sine x over 1 minus sine x. So we got 1 over 1 plus sine x times 1 minus sine x over 1 minus sine x. And we multiply these guys, of course, and we see that this is the difference of squares pattern. So we have 1 times that, of course, is 1 minus sine x, no change there. And in the denominator, we have 1 minus sine squared x. And the real problem here is that we have this, this binomial in the denominator here. And what we're really driving at is we're really trying to get this into a monomial so that we can then do something more useful with our fraction, in other words, get rid of it. So here again, we have a binomial, 1 minus sine squared x, but our identity, sine squared x plus cosine squared x equals 1, comes in handy here, because we see that if we just zip the sine squared over to the other side here, and we get 1 minus sine squared, well, that's the same as cosine squared. So now we have 1 minus sine x over cosine squared x. And now we have a monomial, and you can see how useful that's going to be for us, because when we have a monomial here, we can divide it into this one and into this one. So we write it as two separate fractions, 1 over cosine squared x minus sine x over cosine squared x, which, by the way, I'm going to write like this, just for kicks. Well, actually not just for kicks, but you'll see why in just a second, because cosine squared x is really cosine times cosine. So we know that 1 over cosine squared x, using the reciprocal identity, gets us into secant squared x. And we see this guy right here, sine over cosine, well, we know that's tangent, so that's tan x. And this is times 1 over that, right? And of course, 1 over cosine is just secant x. And there is the whole show written without a fraction. Okay, so there it is. There's the quick video. These are not particularly easy. I know that they seemed easy as we went through them right here, but the key idea here always is to try to make things into sines and cosines, and try to find a way to make only one function in your expression. So if you have bunches of sines and cosines, try to make them all into one, either sine or cosine. So those are the two key ideas for today. Use the identities, know what they are, see the connections between the things, try to change everything into sines and cosines if you can, and change everything into one trig function if you can. So anyway, that's it, and be safe, have a good weekend, and I will talk to you guys on Tuesday.